Hi folks, Dr. Rutner here. This is the video walkthrough for the two sample hypothesis test where we're comparing population variances. Just to refresh your memory and make sure that we're all up to speed on what we're talking about, remember that variance is a statistical measure that assesses how the values in a sample or in a population vary about their mean. So how dispersed they are or how close are they to the mean. So it's capturing something other than that central tendency. And probably a good question to ask is, well, why do we really care whether population variances are different from one to another, one population to another? And there's a fair number of reasons why we might want to evaluate how variances of populations differ from one another. So stock prices is a pretty good example here. Variance in the price of a stock is generally associated with higher risk. So maybe you've got a couple of different stocks with similar mean values, right? So similar um, average prices over time, but one of them stays fairly close to that mean, doesn't vary a whole lot, where the other's way up and down and varying dramatically about the mean. The greater degree of variance indicates a greater degree of risk in owning that particular stock. Another good example is in manufacturing. When you're doing manufacturing, you want to be able to predict what kind of output you're going to get from a manufacturing process, what kind of quality you're going to get, how much waste you're going to generate. A lot of different things you might want to account for or predict for to help plan your process, make sure you can meet demand, those kinds of things. And so greater variance in those production processes makes it much harder to do that kind of planning or forecasting that you might want to do. Um, and so if you have a production process which gives you greater variance, then it's harder to manage than one with less variance. And so maybe you want to compare a couple of different processes and see which are more variable. Yeah, we've talked in class about temperatures here in West Texas. We might have 50-degree swings in a single day, much less from one day to the next. Makes it a whole lot harder to figure out what we're going to be wearing tomorrow. And so we dress in layers a lot in order to accommodate all of that variability in the temperature that we see. Compare that to someplace like, oh, I don't know, Palm Beach, Florida, might have a similar mean temperature or average temperature, but much less in terms of the amount of swing or variation that they see in temperature from one day to the next. So a lot of reasons we might want to compare and evaluate whether the variance of one population is different from the variance of another. So that's what we're about here, and we're going to walk through the process. So let's introduce, first of all, some of the hypotheses that we might set up. We can do, when we're evaluating variances of populations, we can do either a one-tailed or a two-tailed test, similar to what we saw with evaluating means. One of the biggest differences is that we are going to be working with a different probability distribution. We've worked with the normal distribution and the t-distribution with our computations up till now. We're introducing a new one called the f-distribution, and that's going to be what we use to evaluate our hypotheses for variances. And in just a moment, we'll take a look at some of the characteristics of the f-distribution and talk a little bit about it. But just very briefly, to let you know, so you can kind of understand what we're looking at on this slide. Very briefly, the F distribution is a different distribution of what's called the F statistic, and the F statistic is a ratio between two variances. So you can see we'll compute an F statistic based on our sample data. That's going to be the variance of the one sample divided by the variance of another sample. And we will use that to evaluate a relationship between the variances of two different populations. And so that's the basic kind of idea that we're looking at here. Let's take a look at our hypotheses. I've got a two-tailed set of hypotheses listed first here, where what we are hypothesizing is that the two variances of the two populations are equal to one another. And so our alternative hypothesis then is that they are not equal to one another. We can also do a one-tailed test where we are hypothesizing that the variance of one population is less than or equal to another. And the alternative then is that the variance of the first population is greater than the second one. Normally, when we are doing one-tailed tests, testing population variances, we do like to structure our alternative hypothesis as you see it here with a greater than symbol so that we're working in the upper tail of the F distribution. And the reason we do that is just to keep the math a little bit simpler. And like I say, we'll look at the details of the F distribution here in just a minute, and I think that'll make a little sense then. The F statistic or the F distribution is going to be characterized by two different values for degrees of freedom because, again, remember it represents the ratio of two different variances. Those variances could come from samples that have the same size or different sizes. And so we have a degrees of freedom, which is sample size minus 1 for the numerator of that ratio, and then the same thing, degrees of freedom computed as sample size minus 1 for the denominator of that ratio. So two different values that we need for degrees of freedom from our two different sample sizes. And then the last thing I want to mention here is that there is an assumption that underlies the use of the F distribution, and this is one that's actually a pretty critical assumption to be able to evaluate and to know whether this is true. The use of the F distribution to evaluate population variances depends on the assumption that those populations that we're getting our samples from are normally distributed. And the F test is pretty sensitive to departures from that distribution. And so one of the things that you'll quite often be asked to do or want to do is to evaluate that assessment of normality before you use the F test. And you really need to make fairly sure that you've got some evidence that your populations are in fact normally distributed before you rely on the results that you get from the F test. And it's not that a violation of this assumption means you can't crunch the numbers. You could still crunch the numbers. What it means is that you can't depend on having those numbers lead you to the correct result. And so that's really what it's all about. If you have a sample where you're trying to compare variances and you don't meet this assumption, you don't have normally distributed populations, there are other tests that you can do. We'll see one of those, the Levine test, once we get into ANOVA. But for today, we want to introduce how the F test works and make sure you understand kind of the mechanics of it. Just recognize that the F test is very sensitive to this departures from this assumption of normality. So, all right. So with that being said, first of all, or next, I should say, let's take a look at the F distribution. And so what you see here is a graph that shows a bunch of different F distributions superimposed on one another, but they've got some similar kinds of characteristics. And so that's really what I want to focus on is kind of what's similar and what's different between them. First of all, the F distribution is a continuous probability distribution, just like the normal distribution, or the T distribution is a continuous probability distribution. It's a distribution of this ratio between two variances. And as we said, it depends on its shape and its characteristics depend on degrees of freedom for the numerator and degrees of freedom for the denominator. And so these different colored lines and these different colored curves that you see in the chart are essentially different F distributions that vary by degrees of freedom. Now, the other thing you'll notice is that the F distribution starts here at 0 and then goes up to some positive number. This particular chart happens to stop at 5. It could go a little bit further, but this one is stopping here at 5. Now, let me back up to the previous slide for a second because I want to talk about why that F distribution starts at 0. First of all, variances represent squared deviations of values from the mean, right? And so if we're talking about a squared value, we know that each value that we have in this ratio has got to be a positive number. There's no way we can take a value, working with measuring real variables, no way we can take a number, square it, add up all those squared numbers, and get to a negative value, right? So variances have to be positive. We're dividing one positive value by another positive value. So the result, or the F statistic itself, has to be a positive value. And so going back to our picture of the F distribution, that's why the range of this variable starts at 0. You cannot have a negative F statistic. And then it goes up from there. And like I say, we could certainly go beyond 5, but that's good enough for what we're showing here. So the range of, first of all, the F distribution is not symmetric about 0. Its range actually starts at 0. The second thing to notice is that depending on degrees of freedom that we have for the numerator and denominator of that ratio, we have greater or lesser degrees of skew in the F distribution itself. And so the red line here represents kind of the lowest possible degrees of freedom we could have. One in the numerator, one in the denominator, and notice it's extremely right skewed, right? In fact, it really looks more like an exponential distribution than anything else. Very, very right skewed. Move up to 2 degrees of freedom in the numerator and 1 in the denominator. That gives us this black line here, still very right skewed. Move up with 5 and 10 degrees in the numerator and then 2 and 1 degrees in the denominator respectively. That's the blue line and the green line that you see here. Now, this is starting to take on a little bit more of a bell shape, but still a great degree of skew going on, very long tail going off to the right. And so, in no way could you call that a symmetric distribution. Finally, jump all the way up to 100 degrees of freedom in both numerator and denominator, and that's this light gray line. And this one actually is relatively symmetric. There is still some skew to it, and so you would have to get even larger degrees of freedom to move closer to a symmetric distribution. But in general, we're going to be working with things, probably closer to these blue and green lines for our particular F distributions than these very large samples. So the F distribution typically is going to have some skew that we're going to be working with. And so because it has that skew and because it's not symmetrical around 0, it's generally going to be easier when we're doing hypothesis tests to work in the upper tail of the distribution. And so that's going to be kind of the approach that we're going to take. We're going to try and, when we set up our hypotheses, set them up in such a way so that we're working in that upper tail with our region of rejection and determining the critical value of the F statistic. All right, so let's get a little bit more specific here. This is just kind of talking through some of the things that we looked at on the graph a moment ago. We can get a critical value of F from tables that are in your book. We'll look at how to do that, and we'll also see how we can get a critical value of F from an Excel function. F statistics are defined by 2 values for degrees of freedom. When we're working with an F distribution, the way that we can ensure that we are working in the upper tail of that distribution is when we compute the ratio, that F statistic ratio, just make sure we put the bigger of the 2 variances in the numerator of that fraction, which guarantees we're going to have the fraction will have a value that is greater than 1 and puts us up in the right side of that distribution. Remember, we get to decide, we get to assign which is population 1, which is population 2, which is sample 1, which is sample 2. So we just want to pick the one that has the greater variance and make sure we assign that as 1, and so it goes in the numerator of this distribution. All right, so that's kind of some characteristics of the F distribution. Let's go ahead and take a look at how we use it to evaluate hypotheses. And you're going to see that the evaluating a 2-tailed hypothesis and a 1-tailed hypothesis are pretty darn similar when we're using an F distribution. So this first example is looking at a 2-tailed hypothesis where we're hypothesizing that the variances of the 2 populations are equal to one another. with the alternative being that they're not equal to one another. We've got an F distribution drawn here, and this is just sort of a generic F distribution. It's not geared to any particular values of degrees of freedom. And this is what you'll normally see is it's going to be drawn with this tail going to the right to reflect the fact that it typically has a good bit of right skew. What we're going to do in our hypothesis test is select a given value of alpha, and alpha still means the same thing. It's still our level of significance for the test. 0.05 is a pretty normal value with an F test, just like it is with tests of the mean. And it represents the possibility or probability, I should say, the probability of a type 1 error that we're willing to accept in our test. Because we're doing a two-tailed test, we're taking that alpha value, dividing it by 2, and putting that in the upper tail of the distribution, using that to determine a critical value of F that separates that region of rejection from the remainder of the area under the curve, and then expressing our rejection rule in that upper tail. And again, doing that just because we want to work in the upper tail of the distribution. So we're going to reject our null hypothesis if we get an F statistic that is more extreme or greater than the critical value of F for 1/2 of our alpha value. Now, we said that an F distribution represents a ratio between two different variances, and what I'm doing here is I'm setting my variances equal to one another, or I'm in my hypothesis test, I'm postulating or hypothesizing that they're equal to one another. We can also do a little bit of algebra in terms of the way we've written these hypotheses. And so just looking at the null hypothesis, if I were to take and divide both sides of this hypothesis by the variance of population 2, what I would get is I would get a ratio of variances on the left side, variance of population 1 divided by the variance of population 2, and just the value 1 on the right side. And so what we're doing here is we're really expressing the ratio of those two variances in the form of an F statistic. And then the same thing with the alternative hypothesis, just rewriting it, dividing both sides by the variance that was on the right, and so restating our hypotheses here so they look more like the computation for the F statistic. All right, and then for a one-tailed hypothesis, again, remember we get to decide which population is 1 and which population is 2, and we would like to set this test up in such a way so that when we evaluate it, we've got our region of rejection in the upper tail of our distribution. And for a one-tailed test, we're going to put the whole alpha value in the upper tail, find the appropriate critical value, and we're going to reject our null hypothesis. If our test F statistic comes out greater than that critical value of F, and again, we can do a little bit of algebra on the way these hypotheses are stated, and divide both sides by the population or the variance of the second population, and so express those variances as a ratio, like we've done there. All right, so that's the basic set of tests that we're going to go through. Let's go ahead and take a look at an example and walk through the steps, and we'll look up a couple of things and do some computations while we're going here. But the example that we have here is looking at chemical yield from some sort of a chemical reaction process. Maybe we're producing chemicals for industrial processes or something. And we are interested in evaluating two different catalysts. We've got a new catalyst that we think is going to give us lower variability, which means more predictability in terms of our yield as compared to the old catalyst. So the new one is XA100, the old one is ZB200. And in order to evaluate this, we've run a little experiment. And so 5 1-hour periods, we have the results shown in some sort of units. Maybe this is grams or pounds, or I don't know what units these values are measured in, but we've got 5 different results from our 5 different 1-hour periods for each of our 2 catalysts. And so the way we've got this test formulated is we're going to test at a 0.05 level of significance, whether the variance for the old catalyst, ZB200, is greater than that for the new one, XA100. So testing variability. All right, so let me back up here. And I am going to go to, first of all, my write-up. And I think I've got the same problem statement written here in this write-up. And I will post this to Blackboard for you. And we're going to test our hypotheses using the critical value approach. And we're also going to see how we can compute a p-value based on our sample data. So first, stating our null and alternative hypotheses. I just went ahead and stated them as ratios here. I'm doing a one-tailed test because the question that we're evaluating is expressed as a greater than relationship. So that leads me to a one-tailed test. And so I've got the ratio of the ZB200 catalyst to the XA100 catalyst. My null hypothesis is that that ratio is less than or equal to 0, or excuse me, less than or equal to 1. My alternative is that that ratio is greater than or equal to 1. Now, I've already computed the variances of the 2 samples that I've got. Although as I'm looking at this, I think I've got just a typo. These need to be expressed as sample variances and not population variances. So I'll make that correction before I get that posted for you there. But I've got 5 observations in each of the samples. The ZB200 sample has a variance of 44.2. The XA100 sample has a variance of 386. And so actually, I really do want to know what the variances of those 2 samples are before I decide on exactly how to express my hypotheses here, because I want to make sure the larger of those goes in the numerator of that fraction, that ratio. And then, of course, just recognizing here that we have to be able to assume that the samples were drawn from normal populations. All right, I've got this data set up in a spreadsheet, and let me just kind of catch up with the computations here. I'm just going to use a count function to count how many items I've got in each of the samples. In this case, the sample sizes are equal, but they don't have to be. I can use this test with different sample sizes. And then I'm going to compute the variance of each of those samples. Those should be the numbers that I just showed you on the sheet. And then let me copy those formulas over. And I think those numbers should look fairly familiar. Then over here, just to kind of pull stuff together here, I'm going to get my sample size for the sample with the larger variance, which is the ZB200, and then I'm also going to pull over the variance. And only reason I'm going through a couple of steps to do it this way is so that once I actually start doing my statistical computations, whoops, I pulled up the wrong numbers there. Once I actually start doing my statistical computations, I like to have the data in a table that follows a format that you're accustomed to and that you've seen before. So just pulling over the values, so I've got my starting data here in a tabular format. All right, so I'm not going to worry about the F statistic just yet. I am going to go ahead and compute my degrees of freedom, though, for each of the 2 samples. And so that's just sample size minus 1. All right, so I get 4 for both numerator and denominator degrees of freedom. Coming back to my write-up here, the next thing I would like to do is go ahead and figure out how to state my rejection rule. And so we're doing a one-tailed test. So we put all of the alpha value in the upper tail of the distribution. We know that we've got 4 degrees of freedom in both the numerator and the denominator of that fraction. And so we need to know what this critical value is going to be. Now, we have got an F table in the back of the textbook. You can find this. It's table E.5 on page 645 of the, sorry, I've got a friend here that's helping. Page 645 of the textbook. And the way these F tables are set up is that you've got one table for each of a number of different upper tail areas that you might be interested in. So this first one has an upper tail area of 0.05. And then the way the table is organized is that coming across the column headings, you've got degrees of freedom, possible degrees of freedom for your numerator. Coming down the row headings, you've got possible degrees of freedom for your denominator. So in this case, we are looking for 4 degrees of freedom in the numerator and 4 degrees of freedom in the denominator. I realize you likely can't see this on the camera, but if you look in the table at that intersection of those two values, you get 6.39, which is what I have stated in my document. The next 2 or 3 pages show you the F tables if you have 2.5% of the area in the upper tail of the distribution, then 1%, 0.01, and finally, you've got a table for 0.005. There we go. And so you've got 4 separate F tables that have different upper tail areas to use. All right, so that's the looking at the 6.39 or the critical value of F up in the table. We can also make that computation in Excel. And so just as we saw, we had functions in Excel to find F values or normal values, distribute Z values or T values from a distribution. We've also got a function that will do the same thing for an F distribution. We are going from an area, which is our level of significance, and with a given number of degrees of freedom, we want to find a critical value of F. So that's going to be an inverse function that we use. So if I go to my formulas and put in F inverse, I've got a couple to choose from. I've got the F dot inverse right-tailed and the F dot inverse function. F dot inverse gives me a left-tailed critical value, whereas F dot inverse right-tailed gives me an upper or a right-tail critical value. I'm working in the upper tail of my distribution, so I want an F inverse right-tailed. So I'll go ahead and select that. The probability that I need to give it is going to be the probability in the upper tail of the distribution. And so that's going to be my alpha value. I'm doing a one-tailed test, so I give it the whole alpha, not half. And then I need to tell it how many degrees of freedom I have in the numerator and how many degrees of freedom I have in the denominator. And those are a couple of the values that we'd computed. And so that gives me a upper tail critical value of 6.3882. That rounds to the 6.39 that we had looked up in the table. So we're able to confirm that value. We're pretty much always, because we're going to set things up so we're working in the upper tail, pretty much always going to be using F inverse right-tailed to find a critical value of F. All right, then we need to go ahead and compute our test statistic. And so we will again, and I say I've got the same typo here, I've got sigmas instead of S's for my variances here. We're going to compute the F statistic for our, based on our sample data by taking the variance of the ZB100 set of reaction times or production values and dividing by the variance of the production values for the other. And so I can compute my F statistic by simply taking the larger variance and dividing by the smaller one. That gives me an F statistic of 1.2544. Comparing that to my critical value, I can see that my decision is going to be that I do not reject the null hypothesis. At the 0.05 level of significance, there is not enough evidence to conclude that the variance of the new catalyst is less than that of the old catalyst, or stating it in the opposite form, there's not enough evidence to conclude that the variance of the old catalyst is greater than that of the new catalyst. All right, so that's walking through the critical value approach to doing the F test. We can also compute a p-value. And let me go back to my write-up here. A p-value means the same thing here in the context of an f-test as it meant in the context of a t-test or a test using the normal distribution. P-value represents the probability of getting a test statistic at least as extreme as the one that we got if our null hypothesis is true. So in this case, it's going to be the probability of getting a f value greater than 1.2544. And so in order to compute that, we can use the f distribution function. And so remember, if the kind of function that we want to use when we are going from a value of f to a probability is going to be an f distribution function, just like we use norm dist to go from a z value to a probability. We use t dist to go from a t value to a probability. We used f dist to go from an f value to a probability. And again, you've got a couple of different versions. You've got f dot dist, which gives you a left-tailed probability, f dot dist right-tailed. We're working in the upper tail of our distribution, so I want f dist right-tailed. And the values that I need to give to it are the f-test statistic and the 2 degrees of freedom for the numerator and for the denominator. And so what that tells me is with 4 numerator and 4 denominator degrees of freedom, the probability of getting an F statistic of 1.2544 or greater is actually fairly high. It's actually 0.4157. And since that p-value is greater than my specified level of alpha, we will not reject, we fail to reject the null hypothesis, and that confirms the result that we got with our critical value approach to testing that hypothesis. All right, so that's working through a one-tailed example using the F distribution. If you were to set up a two-tailed hypothesis, then pretty much everything is going to be the same with just a couple of small changes. And you can see those changes in the formulas that I have written out here. The changes really are that when you compute your upper critical value, instead of having the entire alpha value in the right tail of your distribution, you're only going to have half of that alpha value. I'm just going to go ahead and compute these values here, even though we're doing a one-tailed test. But just to show you how I would make that change, I would just divide alpha by 2 here, and then I'd still give it my same degrees of freedom. All right. And so what we would get is we would get a larger value for our critical value. Our critical value would move over to the right because it's segregating off a smaller area in that upper tail. And then the same thing with the p-value. The easiest way to get a p-value for a two-tailed f-test is just to take the p-value we computed for the one-tailed f-test and multiply it by 2. Simplest way to make that computation. So what I'll do here is I'm actually going to go ahead and set up my f distribution right-tailed function first. And so I'll give it the statistic, the f statistic based on my sample data, as well as my 2 values for degrees of freedom. And then I'll go in and I'll just modify that formula to multiply the result that I've got by 2. And so you can see I'm coming up with a larger p-value because this p-value accounts for the probability of getting a test statistic at least as extreme as what we got in 2 different directions, in both directions, not just in a single direction. And that's the way we do it for a two-tailed test. All right, so that kind of walks us through the process of doing an f-test to compare 2 variances. And I'm going to do one more video for y'all, and that will be looking at using some tools that are already set up in Excel to confirm what we've seen.